I'm Praharsh Singh, and this video is a part of my DSP lab report. So, in this video, I would be calculating the heart rate and the pitch of a speech signal uh, using autocorrelation function. So here we are given the offline. I would be conducting the event in an offline mode. That is, I would be given the signals. So here is my PPG signal, digital PPG signal stored in the X array. And now I will be explaining the code. So here's the X array in which the PPG signal is stored. The Y array stores the Y array is the temporary variable array, which we basically helps us in coding or signal processing. So then we define L, which is the length of the size, which is the size of the array, one which is basically 150. Then we define L1 equal to 4. This is the moving average filter window size L1. Then we basically move on to the first iteration of the code, which comes in void setup. So now central.begin, this is the baud rate for our Arduino board. Now moving on, we define first we used the moving average filter. So moving average filter to remove any high frequency noises. Now moving on, so we define a variable sum equal to 0, and in this filter we basically calculate the sum of the window size, average of the window size, and then put it down to the our original element of the array. So this code basically does that for us. And the for it would be only valid if I is I minus j is greater than equal to 0. That is, the window size is greater than equal to L. So basically, for if we are moving from the start, so we wouldn't be calculating the sum of the first two or three elements, and later on we'd be calculating the averages and putting it down to the below array or the changed array. So this is how moving average filter works. Then moving on to the part of the correlation. So here's the autocorrelation for the function. So I'll be explaining that. So this array would be starting from 0 to L, and with the increment of 1 with each iteration. So now we define float sum equal to 0, and basically autocorrelation function is defined as the the correlation of the function or signal with itself. So to do this, we use the following algorithm. We take the a window size of m, where m is the mth element of the autocorrelation function. So for r0, we have a window size of 0. So basically we would multiply each element with its predecessor element. So basically r0 x0 into x1, then plus x1 into x2, plus x2 into x3, plus x2 into x3 into x4, and so on. Then r1 would be x1 into x2 x3 plus x2 into x4 plus x4 into x6. So basically the window size increases from 0 to n and 0 to L. So this right here does that for us. This expression tells us sum equal to sum plus x times j and x times j plus I. So j plus I gives us that window. So that window, it basically propagates throughout the array until there is no there until the array ceases to exist, and thus we get the Rm, or the autocorrelation array, which we stored in yi. So uh, that's the autocorrelation code. So now we'll first plot the autocorrelation array, and then we will discuss further. So this code basically up till here plots us the autocorrelation array, and so let me run it. Okay, so I changed it here, sorry. So this is the autocorrelation function, in the red line. So now we can observe that we are interested to find the this position, this length, basically of this autocorrelation function. So this function through this length, through this length or the element nth position where this peak occurs, we would be able to calculate the beat rate of the person or the signal. So to calculate this peak, first we would use the following algorithm. We would first calculate the zero crossing point. So first we would calculate this point n, then after that we would try to calculate the maximum height of this function. So that would basically give us this maxima. So now to do that we would go to the following code, and that is here. So first zero crossing point, this is that. Then to calculate that point, we would state that y of I, if y the change the autocorrelation in the autocorrelation function, if yi is greater than 0 and y of I plus 1 is less than equal to 0, basically the curve goes from here like that and to here. Let me just plot it again for you. Mm. So basically when this point goes from this location to this location, uh, that would be our fzcp. So fzcp is stored here. So let me let me calculate the fzcp point. So for fzcp point, this is basically the y or autocorrelation function, y array. So and the 11th I equal to 11th position that that occurs. So we have calculated the fzcp. Now we would calculate the next high maximum point. So now moving on, so we would calculate the peak index, so the index of the peak from the zero crossing point. So let's define it as peak index zcp equal to 0, and also peak index equal to we define peak index as int. So now moving on, for int I equal to fzcp from the fz0 zero crossing point to the 150th to the lth position, we will be calculating uh, this algorithm, will be running this algorithm. So if yi is greater than the peak index from zcp, so the ith element is greater than the peak index from zcp, peak index equal to I. So the index of the peak would be I, and the peak index from zcp equal to y of I. So basically would be storing that y of I. Then uh, so basically this would give us the peak index. So let me uncomment this and rerun it. So this gives us so this is as peak index at 47. This basically means that the 47th position is the our required position. So to calculate the beat rate, we use the simple formula period equal to 50, that is the sampling frequency, into 60 because we are interested in beats per minute rather than beats per second, divided by peak index. So let's run this. So it caused an error due to mistake. So here we'd be using the print align, so it would change the line for the next parameter. So in the next line it would print our heart rate or the required function, the heart rate of the required function. and then we shall find it again, and basically we get a value of 63. So this concludes the ppg signal part of the experiment. So our heartbeat was recorded as 63. And so now would be moving on to the audio speech signal part of the code. So here we would first process this signal, process the audio signal into a MATLAB file, through a MATLAB file, to obtain the digital data. So now we'll be using the these commands to clear the temporary variables and the command window. So now we can see that we have y comma sr, and this is read through an audio read file, a command of the MATLAB tool. It reads the file. This is the location of the files. It uses Praharsh desktop e.wav. This is a .wav file. So in y array, in y we have the digital data, and sr is the sampling rate. And now we we give csv write. So this basically writes the y. So now we would be having the our digital data into y array. And now we would be taking the transpose of it to convert it from the column array to a row array. So now I am using MATLAB because the Arduino that we have, the Arduino Uno, is not sufficient enough to process the 8000 samples simultaneously in a go. So hence I would be using the MATLAB tool to calculate the pitch of the signal. So now basically I would be employing the autocorrelation function and using the same algorithm and same techniques. So now moving on. So I define through array y equal to zeros. 1 to 8000 basically creates a zero, temporary array is y of 8000 length, which have all zeros in it, and t of 8000 length of all zeros in it. Then moving on, uh, we have for I equal to 1 to 8000, t of I equal to I. So basically in t array, each element we will have the length of 1 2 3 4 up to 8000. Then we define L equal to 8000. That means we are processing 8 data which has 8000 length. And then we define max, which is the maximum in this audio read file. So max equal to max of x. This max function gives us the maximum element that the x has, and this basically is the normalization operation. So it would be normalizing our audio speech array. So x now would be a normalized version of this array. Now moving on, for we would be using the autocorrelation function. So for I equal to 1 till l, 1 till l, this means 8 up to 8000. This will increment in steps of 1 if it is not specified. So now we have defined sum equal to 0, and for j equal to 1 to l minus I, and this basically does the autocorrelation function. So each time we would be calculating the sum of each of the components with the window of m. So where m or j, with the window of j, where j is the where j is the jth element, j is the element of j is the window element of the autocorrelation function. So basically, if we are calculating R3, then we are interested in R1 and R4. Then R1 R4 multiplied plus x1 x4 multiplied plus x2 x5 multiplied plus x3 x6 multiplied. So it goes on up till the end up till the end, that is L 8000, up to 8000 characters or array size. And that it would be storing that function into a yi, that is the autocorrelation function array. Then would be plotting the y. So plot t comma y. So t is the is the zeros of this this t that we define for which has the values from 1 2 3 4 5 6 up to 8000. So this basically gives us the curve of the autocorrelation function. Then would be using let me plot it once. So by running it we can see that we are having the the array. This is the array, it goes on above also, and besides that we have this curve. So this is our autocorrelation function for the audio speech signal. Now we are interested in this peak. So to get this peak, we would evaluate our data. So first we would find the zero crossing, and then would be calculating the peak, and then we would be calculating this whole length. So to do that, we first find the zero crossing. So first we define an variable zero cross equal to 0, and if y is greater than 0 and y if the next element is less than I less than 0 and the ith element is greater than 0. So basically we are interested in this point somewhere around here. That means this is greater than 0 and this is less than 0. So we will get the zero crossing point from that. I've printed out the zero crossing point as zero crosses L11, so we would get the 11 as the zero crossing point. Now we'll define as mx equal to 0 and mx index equal to 0. So now moving on, this would be required for the calculating the pitch. So uh, so there are some changes that is required, so I'll make it that first. So basically is pitch equal to the sampling frequency is 8000. So it's basically L or SR, sampling frequency, divided by the mx index or the length of that array. So we would get the pitch. So now first let me explain how to get the mx index. To get the mx index, we will simply calculate the max. So to calculate the max, here is the code. We get set mx index equal to I and mx equal to y of I. So if y of I is greater than mx, so let me plot it once again. So we would be calculating if y of I is greater than mx value, then it would be updating itself to that value until it has the largest value, that is this value. So now it is getting the ith element, mx index element I, which has the maximum peak. So it be storing that mx index, and let me run it again. So oh sorry, don't print it. So now we are getting our pitch equal to 228.5714 hertz, and this is our mx index that we printed out. And pitch is basically the sampling frequency divided by the mx index. So mx index is mm, mx index we calculated in this part of the code. So hence this concludes my experiment number 12, experiment number 3, speech recognition and ppg bit rate evaluation using the autocorrelation function. Thank you.